The James Webb Telescope continues to produce images that show something is wrong with our universe, or our space is going crazy. This could mean it has some kind of intelligence, or our scientists have simply been mistaken. The fact is that, since the launch of the new telescope, we are experiencing an unprecedented crisis in world science. It seems the new discoveries are trying to tell us something urgent, but so far, scientists are arguing more than they are presenting us with new facts and real truths. Does this mean the end of everything? Nothing has been left unexplored. Since the JWST showed us images of such ancient and perfect galaxies that shouldn't even exist, it marked the beginning of a drama in modern science that continues to this day. More and more images show even crazier and impossible phenomena. Nothing in the young universe is as scientists thought it was, and now it's also clear that the entire universe isn't as our scientists thought it was. So far, researchers have hypothesized that the universe was homogeneous, meaning its large structures have a broadly uniform shape. But now there are dozens of indications suggesting that the universe is actually inhomogeneous, and this challenges some of the basic assumptions about the nature of the cosmos. The idea of a homogeneous universe dates back to early 20th century cosmology. Albert Einstein introduced the cosmological constant in his general theory of relativity, describing a static universe that neither expands nor contracts. Shortly thereafter, it became clear that we do not live in a static universe, but that this space with all its phenomena is highly dynamic. There is nothing that doesn't move in this universe. However, physicist Alexander Friedmann concluded that Einstein's field equations also work with an expanding or contracting universe. Georges Lemaitre then proposed the idea of the Big Bang, where the universe expanded from a single point. These developments led to the idea of a homogeneous and isotropic universe, based on the so-called cosmological principle. The principle states that the universe is homogeneous and isotropic on a large scale, meaning it looks the same everywhere regardless of where you look. Let's make a comparison with a landscape. A homogeneous and isotropic landscape would be like a vast infinite desert where the sand is evenly distributed everywhere and where there are no hills, valleys, or other geographical features. No matter which direction you look or where you go, the landscape looks the same everywhere, and there are no preferred or special places. In the case of the universe, this means that stars, galaxies, cosmic nebulae, and other phenomena are approximately uniformly distributed in space. However, recent discoveries by the James Webb Space Telescope and other astronomical observations have shown that the universe may not be as homogeneous and isotropic as previously thought. Quasars and the Great Ring demonstrate this. It may be strange to imagine the entire universe as a landscape, but looking closely, the idea is not so far-fetched. Only the dimensions are a bit larger. We have galaxies with millions or billions of stars wandering the universe along filaments and gathering in groups. We know of gigantic voids, black holes, and other phenomena. All these objects participate in the cosmic spectacle. Researchers have now discovered that one side of the sky has about 0.5% more quasars than the other. Quasars are extremely luminous galactic nuclei powered by supermassive black holes. This inhomogeneous distribution further suggests that matter in the universe is not uniformly distributed. The second discovery that goes against the theory of a homogeneous and isotropic universe is represented by two extremely large cosmic structures, the Great Ring and the Giant Arc. These are phenomena formed by galaxies and clusters of galaxies. These structures are so large that they exceed the scale on which the universe is supposed to be homogeneous and isotropic. Practically, they are so large that our measurement techniques fail. These structures demonstrate the existence of something like high mountains in the universe's landscape, which currently no one knows how they emerged or fit into the overall structure. But these are just the latest discoveries that are slowly but surely strengthening the suspicion of a heterogeneous universe. Before these latest exciting discoveries, there were already clues from the different expansion rates of the universe. In this case, different methods of measuring the expansion rate of the universe yielded different results. This difference is known as the Hubble tension. If the universe is not the same everywhere, this would explain why it is not expanding uniformly. Somewhere between the levels of cosmic background radiation and Cepheids, there may be a previously unknown layer of the universe or a force responsible for the measurement differences. Or the universe is not expanding uniformly because there is a cosmic mountain somewhere in the middle. Again, the new telescope plays its role in current research, as scientists have used the JWST to confirm the Hubble tension. Why does cosmic background radiation show a uniform distribution of matter? Do you want to know a really curious fact and a fantastic theory? Let's take another look at cosmic background radiation, CMB for short. It indeed shows a uniform distribution of matter. The CMB is considered the glow of the Big Bang and is essentially a uniform microwave radiation. The radiation originated around 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine to form neutral hydrogen atoms. This moment is known as recombination. Before recombination, the universe was a hot, dense plasma of ions and electrons that constantly collided with each other and scattered photons. These constant collisions ensured that matter and radiation in the universe were tightly coupled and in thermal equilibrium. During this period, radiation was strongly scattered by the dense matter, preventing it from traveling long distances without encountering particles. As the universe continued to expand and cool, temperatures dropped below about 3000 K, allowing electrons to combine with protons to form neutral hydrogen. This process drastically reduced the number of free electrons, making the universe transparent to photons. Photons could finally travel unhindered, light was created, and the decoupling between matter and radiation continued. These released photons are what we see today as cosmic background radiation. The uniform distribution of CMB radiation led scientists to believe that the universe was almost homogeneous and isotropic. Perhaps it was more than 13 billion years ago when it was smaller. But now imagine, what if the universe is not expanding into empty space, but into space where something already exists? The Big Bang and the distribution of matter shortly thereafter might have been homogeneous. But then the expanding universe encountered obstacles that interrupted the homogeneity. These obstacles can be many, but all lead to fantastic theories that excite space enthusiasts but give scientists headaches. The old knowledge about the Big Bang says that space was born only with the Big Bang. The expanding universe is space. According to the old theories, nothing exists outside this space. Quantum physics has already proven that nothingness cannot exist. Moreover, it has shown that a multiverse with many nested dimensions and countless universes of different shapes, sizes, and natures is more likely than the single universe we live in. What if our universe expands into space where other universes, dimensions, and previously unknown structures exist? This would obviously mean that, during its expansion, it encounters obstacles, pushes away other universes or dimensions, or these exert resistance on our universe. An initially homogeneous Big Bang would then become inhomogeneous due to these encounters. These considerations are interesting, but despite numerous astrophysical inconsistencies, they currently receive little official attention. Our Earth is proof of this. You won't believe it, but some brave researchers supporting theories like the multiverse have proposed an interesting comparison. Our Earth also began as a homogeneous world. Planets, in their early stages, are collections of gas and dust, just like early suns. Then they slowly develop, become more independent, take on an individual shape, wander within the solar system, collide with other celestial bodies, and change. At first, Earth was a hot, glowing ball, and matter was evenly distributed. Then a heterogeneous structure developed, at least on the surface. We have large oceans and land masses that are not necessarily evenly distributed on the globe but more randomly. The Eurasian continent is huge, just as Africa is almost directly adjacent, while the American continents are elongated and thin. We also have more heterogeneous structures within the oceans and continents. Deep crevasses and trenches, shallow stretches, lagoon seas, etc. On the land masses, deserts, high mountains, densely populated areas, and sparsely populated regions have formed. But what can we learn from this heterogeneity concerning the universe? Well, our Earth demonstrates very well that the planet has changed over millions of years, from a homogeneous world to a heterogeneous one, at least in part. At least rocky planets all show traces of such changes. Even Mars, Venus, and Mercury have heterogeneous structures, albeit not as extreme as on Earth. If we look at the rest of the solar system, gas giants are more homogeneous and have probably not changed appearance for millions of years. But the diversity of our planets once again shows you the non-uniform distribution of matter and gas within the solar system. If we return to the landscape of our universe, it is quite conceivable that a cosmos takes on heterogeneous features over its evolution. And we have to reckon with the idea that our universe is an even more dynamic entity than we thought. The latest discoveries of the James Webb Space Telescope have shown that our science has been wrong in many ways. Old cosmology is crumbling, and perhaps now we should recognize that even physical forces undergo evolutions and changes over time. Thanks for watching, subscribe now, and stay tuned for many more exciting videos.